So I work mostly in experimental laser and photonics, right? So like my PhD work was on the synthesis of nanoparticles using lasers, high power lasers. And then I also worked on the dynamics of the processes that are involved. So I use shadowgraphy, beam deflection, and certain techniques, all laser-based techniques, to study the phenomena of cavitation bubbles, shock waves, etc. So that is, mostly about my research work. So today, what I'm going to do is I am going to continue with classical physics. But again, I'm sure most of the important topics have already been covered by Dr. Sheetal. And my favorite topics are also the Hamiltonian and Lagrangian, all of these, because anyone who is interested in physics, I'm sure that person would agree that these are some of the most fundamental topics, and liked by all, right? And because they never fail to fascinate us. So again, my task was again, I had to cover a bit of rigid body dynamics, and then tomorrow I'll be talking in brief about with some examples about the relativity. So special theory of relativity, I'll be talking about simultaneity and all. So today I'll be talking about, yeah, rigid body, as I said, and then tomorrow I'll be introducing the special theory of relativity. So now, first of all, again, let me tell you, in one lecture it is not possible to cover rigid body, right? So I thought, let me, because you all are from different universities and different institutes, right? So the basics that you should be knowing, right? So I'll try to recap kind of thing. And then what really is this rigid body. And if you have heard about the Euler angles, so we'll talk about how the Euler angles came to the picture, right? So what was there. And of course, later on I'll I would encourage you to refer to certain books, which would kind of you are not left on your own, right? It's because these books are, it's kind of a guide for us, right? So when Aziz would know that when I was teaching them electricity and magnetism, so I introduced them to Griffith, right? So and that I'm sure it is not possible for me, in fact, in a particular semester also, to cover the entire Griffiths. But what I try to do is I try to make the students feel comfortable with the book, so that later on, of course, they can always come to me. But if they are familiar, some the approach that is adopted in the book, if you are able to grasp that, I think most, that is the major task, to just show you the path, and later on you have to work on your own. So similarly, so first of all, let us talk about what is this rigid body. So can someone tell me what this rigid body is? Correct, right? So fixed distance, that means it is yeah, constraint is the keyword, right? So we'll talk about all of these. We'll start with this. So rigid body, my screen is visible to everyone online, right? Can someone say yes? Yes, I won't ask any further questions. Yeah, okay. Yeah. So, okay, thank you so much. So rigid body is, going by the definition, it is a system of mass points that are subject to constraints, right? As rightly said by, what is your name? Shubham and Amia. Okay. As rightly said by Shubham, that, it is subject to constraints that all distances between all pairs of points, they remain constant throughout the motion of the body, right? So that is the basic definition of your rigid body, right? And of course, if you know, this is an idealization, right? This is an ideal concept. And however, as you must be aware that, it is very useful. It helps us understand a lot of physics, right? So that are involved. And when we talk about rigid body, so the study of rigid body is divided into two parts, right? So one is the kinematics of it and the dynamics, right? So initially I thought I'll be covering the, kinematics in one class and the dynamics in other, but again, I thought, it will again not be, I won't be able to do justice to that, right? So I thought, I'll introduce some concepts of, the kinematics part, And for this, what I would suggest is, I have referred to, what book, which book comes to your mind when you talk about classical mechanics? Goldstein, right? So, I have referred to Goldstein, and the fourth and the fifth chapter of Goldstein is, on rigid body dynamics, right? So, and there are multiple, n number of books on classical mechanics. You can refer to any of these, but if you make, the Goldstein's book the base, so you will, never, you will never be deprived of any, particular concept in classical mechanics. That is what I feel, right? So first, the kinematics. So what is kinematics? It is basically the description of motion without discussing the causes, right? So in kinematics, we don't, we discuss about the motion, whatever is taking place, but we are not concerned about the causes. Now, what are these, what are the dynamics? What is it? Here, we talk about, or we study the causes of motion. So for example, we talk about the forces, the angular momentum and torques, etc. Right? So, and first of all, first one, that is, kinematics is very mathematical. So again, the fourth chapter in Goldstein, it is dedicated mostly to, in introducing the various tools that are available. And then in the dynamics part, the fifth chapter, those are directly being applied, right? So, to understand the concept of inertia, tensor and all, so it is used, right? So now, in this definition of rigid body, so you come, as Shubham said, Shubham spoke about the constraints, right? So, but within bracket, if you can see, there is something called holonomic. Now, what are holonomic constraints? Can anyone?
Like reduces the degrees of freedom.
Okay.
Without any.
Correct. Oh, so you know more.
Coordinates such that they can be written as a function which is equated to 0.
Correct. Right. Absolutely correct. So can someone online also tell me, what do you understand by holonomic and non-holonomic constraints? See, you may be wrong, but, please try, I would be happy if you are, trying. I'll come to, I'll show, with examples how, what are holonomic and what are non-holonomic constraints. But before that, can someone please try online? Anyone? So you can say, I don't want to, yeah.
Sir, holonomic constant is dependent on the function of positions, and non-holonomic constant also depend on the velocities of time or existence depending on time.
Okay, there is a lot of disturbance. I'm unable to understand what you are saying, but that's okay. At least, may I know your name? You have tried.
Sir, now am I audible, sir?
Yes, yes.
Now sir,
yeah.
I'm Aviru from PDEU,
Okay.
Physics department. I am doing MSc first year. And sir, I think as far as I remember, I may be wrong. The holonomic constant is dependent on the position coordinates.
Okay.
And the non-holonomic constant is explicitly dependent on time coordinates and velocity coordinates also.
Right. So as you have seen, like the same things can be described in various ways, right? And that is the beauty of, classical mechanics. So, and you will see that, I teach you the same topic. So another teacher comes and, teaches the same topic. You will see that, there is, remarkable difference in the approach that is there. And, that is why, let us, I'll just, these are very common examples. With these examples, because I'm sure, some of you are still not, very clear about what are holonomic and non-holonomic constraints. So first of all, first example is about a pendulum, right? So, I'm calling this as a mathematical pendulum. And here the concept of holonomic constraint is there. And in the second one, you will see any other example that you can, think about. So it can be expressed in terms of the non-holonomic ones, right? So first of all, an example of holonomic constraint can be seen in a mathematical pendulum. As you can see in the first figure, the swinging point on the pendulum has 2 degrees of freedom, right? it can swing, of course, if there is no wobbling agar nahi hai, so you will see that they have 2 degrees of freedom, x and y. Now in this, the length L, length of the thread, which is holding your that bob, so that is the length of the pendulum is the constant here, and we can write this constraint in the form of an equation like it is showing here, right? So that is your x square plus y square is equal to L square, or minus L square is equal to 0, right? So whatever. So this is an equation that only depends on the coordinates, as rightly said by all 4 of you, right? So furthermore, it does not explicitly depend on time, right? So as you can see in this equation, so there is no explicitly, it is not mentioned about anything is mentioned about the time. And this is also known as what? If it is not exclusively dependent on time, so these constraints are also known as scleronomous constraints also, right? And with this constraint, the number of degrees of freedom becomes 1, right? So that is your example of your holonomic constraint. Is it clear, everyone? Fine.
Yes, sir. Clear, sir. Clear, sir.
So next comes your non-holonomic, right? So if you now look into the second, figure, you'll see that, what are these? So as it says, when the constraints cannot be written as an equation between the coordinates, but often as an inequality, like you rightly said. So if you can see in this example, what is this? A non-holonomic constraint is a particle that is trapped in a spherical shell, as is shown here, right? In 3-dimensional space, this is a sphere, right? So this is a 3-dimensional space. The particle then has 3 degrees of freedom, one particle, 3 into 1. So 3 degrees of freedom. The constraint says that the distance of the particle from the center of the sphere itself is, it has to be always less than your capital R, right? Which is the distance of the sphere, right? Or radius of the sphere. So this can be expressed as square root of x square plus y square plus z square is less than R, right? So we cannot rewrite this to an equality. And so this is non-holonomic, as well as it is also known as here, this is again a scleronomous or constraint, right? So that is your different major difference between your holonomic and your non-holonomic constraint, right? So now we will be talking about, and in between, if you have any queries, any doubts, you can stop me in between. Okay, feel free to do that. Yes.
Can I ask something?
Yeah.
So as it is rightly told that the holonomic constraints can be written in a form of equation, in a form of function equal to 0. So as you gave the example of a particle that is constrained in some spherical wall, in that the whole spherical region. If we constrain that particle on the surface of the sphere, we will get some equation of the term f equal to 0.
Correct.
So that will be a holonomic constraint, right?
Correct.
So, but if we consider that spherical surface as a 2D planar projection, so that will reduce to a non-holonomic constraint.
Correct. Absolutely. So now here the point is that, what we are talking about, the distance, between the center, right? So origin and the surface, right? So in that case, so that entire thing becomes a non-holonomic constraint.
Yes.
Right. So that is what the point is, that it is restricted to move within that sphere itself.
Yeah.
So there is an inequality now. So x square, square root of x square plus y square plus z square is less than R.
But if the particle moves on the that is only restricted.
Right. So in that case, you can write that as equal to R.
Yeah.
Right. So in that case, that will be, if that we are able to write it in the form of an equation, then we can say that that is a holonomic one only. So it reduces to the holonomic one in the limit of your that, when it becomes an equality. Right. Right. So that is the maximum limit, or that is the boundary, you can say. So on the boundary itself, there you can apply the equality. So that then it reduces to the holonomic. Right? Yeah, think about it. Yeah. So in fact, Griffith, there is a very nice discussion on this. So, you can again refer to that. Right? Okay. So now coming to the independent coordinates. Right? So how many independent coordinates does it take to describe a rigid body? You know how many? Right? Right. Right. So, you can also put it in another way, that how many degrees of freedom are there? Right. So these are some of the common examples, or common questions. So as rightly said again, so there are 6 independent coordinates or degrees of freedom. So 3 are what? 3 are the external coordinates to specify the position of some reference point in the body. So which usually, we take as a center of mass, with respect to what? With respect to the arbitrary origin that we have already chosen. And number, 3 more, we have the internal coordinates, right? So that are there to specify how the body is oriented with respect to the external coordinate axis, right? So, when I say, in terms of words, again, this is difficult to visualize. So, let us see, we'll see, in terms of figure as well. So before that, let us talk about, suppose I have a rigid body, right? So, and some numbers also we should be knowing, how we can express this. So if there are n particles in that rigid body, right? So how many degrees of freedom I can have there? 3 into n, right? So if there are 1 particles, as I said, 3 into 1, so 3 degrees of freedom. Now, however, constraints are that the distances between each particle pair are fixed, right? So that those are the constraints, and all the constraints that I have, they are of the form what? They are of the form Rij, right? So Rij is what? It is the distance between the particles, that means the ith and the jth particle, and that distance is constant, which I am calling as Cij, right? Which is a constant, right? So this I am marking as your equation 1, right? Now there are n particles, okay? So how many number of pairs would be there? So that would be given as half n number of particles into n minus 1, right? So say for example, you have 3 particles, right? So how many number of pairs would be there? 3. Right? Yeah, right. So now from that, if you just roughly say, what are the number of degrees of freedom, right? So 3 into n is 6 minus 3 pairs, right? So S, that is our number of degrees of freedom, becomes what? We can say that, 3n minus np, right? Degrees of freedom, that is given by this. So 3n matlab ho, kitna? How much is it? 6, right? 3 into n, 9, minus the pair, number of pairs is 3, right? So naively we can say that, the number of degrees of freedom are given by 3n minus the number of pairs np, right? So is this true?
It might happen that some of the constraints are redundant because the number of particles is smaller.
Correct, right? Right. Still 7, there is no problem. Right, right. So that is what I'm saying, that. So although, naively for the initial values, this seems to be true, but when we go, for higher numbers, so say for example, so all equations 1 are not independent of each other, like you rightly said. So also when you put your n, say, it is greater than or equal to 7. So let us take n as 7. So in that case, what is your value, number of pairs?
21.
Right? So 21. So in that case, just what would be the, degrees of freedom? Right. Right. So that is again, so we come to something. So that means when I naively say something, that, the number of degrees of freedom are given by 3n minus np. So this is not true in general, right? So it may be true for the, initial values, but not so. And similarly, your np, the number of pairs, become much, much greater than your 3n, right? So when your number of particles becomes much, much greater than your 1, right? So these things you should keep in mind, okay? Now, so this is what we are talking about, right? So to fix a point in a rigid body, it is not necessary to specify its distances from all other points in the body, right? So it is not necessary, you have to specify all the points, right? It's only necessary to specify distances to any three non-collinear points, right? So you cannot take, collinear points, non-collinear points, three at least. If you take, then your purpose is solved, right? Like you can see here, this is your 1, this is your 2, and this is your 3, right? So, and the distances between them, so they are constrained by this, that is your R13. So between 3 and 2, we have R23, and between 1 and 2, we have R12, right? And this is some other particles, which I'm calling as the ith. So the location of a point, in a rigid body by its distances from 3 reference points, right? So now look into the figure once more. So if the positions of 3 particles are given, in that case what happens? The constraints fix positions of all the other n minus 3 particles, right? So like you can see here, right? So now that is, we must have what? We must have number of degrees of freedom as less than or equal to 9q, because we have 3 into 3, right? So 3. So however, the 3 reference points are not all independent, right? But are related by equations like the one that I showed in equation number 1, that is the constraints that I showed, the distance between 2 particular points. So those were R12 is equal to C12 is equal to constant, R23 is equal to C23 is equal to constant, and R13 is equal to C13 is equal to constant, right? So this gives your S is equal to, because we have this 3, so we have your S, that is the number of degrees of freedom, as equal to 6, right? So now we can also view this, when we say that S is equal to 6, we can view it in another way also, right? So like, first of all, to establish the position of one reference point, so we need 3 coordinates, correct? Now, if I fix one point is fixed, so what will happen? 2 points can be specified by 2 coordinates. So since it is constant to move on a, if I have 2, so it is constant to move on a sphere which is having a radius R12 is equal to C12. So now what happens? With 2 points determined, if I have already determined 2 points, point 3 needs only 1 coordinates, and that is what? Since R13 is equal to C13, R23 is equal to C23, so they constrain its location. So in that way, we can say that pehle ke liye we need 3, second one needs 2, and then the third point needs only 1. So in this way also, we can talk about the degrees of freedom, right? Okay, right? So, but there are different ways of, expressing these as well, right? So a rigid body in space needs 6 independent generalized coordinates to specify its configuration and to treat its dynamics, no matter how many particles is containing in it, right? So that is how it is. Of course, you have to keep this point also in mind, that there may be additional constraints on the body which reduce the number of independent coordinates further, right? So that can always be there, right? So you have to keep that in mind. Now, how are these 6 coordinates assigned? That is the major task, right? So how it is normally done. So configuration of rigid body is completely specified by locating a set of Cartesian axes, right? So Cartesian axis, right, everyone, right? So X, Y, and Z, that the normal ones that we take, right? So they are axes fixed in the rigid body, right? So which I am, I'll show in here, right? So as you can see here, so this is the axis fixed in the rigid body itself, right? So as this is my rigid body, so these are the primed ones, right, fixed in the body itself. So that is relative to an arbitrary set of Cartesian coordinates, which are the unprimed ones, right? So these are the unprimed ones, right? So what happens? So this gives us a space or left frame or reference axis, we may call. So this is fixed in the external space, right? So this is fixed in the external space, right? So this is your primed one, right? And this is your unprimed one, right? So we are going to discuss on this now. Now, look into the figure carefully once more. So you'll see that there are 3 coordinates, right? 3 coordinates, first 3, of course, we'll come to the next 3 also. So 3 coordinates out of the necessary 6 that we require, the generalized ones. So they specify what? Specify origin of body, right? So origin of the body, kahan pe hai? And then axis in space, which are the unprimed axis of the system, right? So these are the 3 coordinates here, right? And the 3 other coordinates, they specify what? They are specifying the orientation now, right? So when I talk about this orientation is the keyword, right? So this will, bring us to the Euler's angles later, right? So specifying orientation of the primed axis, that is the orientation of these particular axes with respect to this, right? Orientation of the primed axis relative to the unprimed axis, actually to the axis parallel to the unprimed axis by sharing origin, but sharing origin with the primed axis, right? So, it is sharing the origin. Now focus on the 3 orientation coordinates that I have, right? So let us focus on this now, right? So as I said, there are many ways to specify the orientation of the rigid body, right? So there are many ways to specify orientation of one Cartesian axis of set of axes with respect to another with a common origin. So the common procedure, can anyone tell me what is the most common procedure that are used?
Sir, diagonalization of the moment of inertia and matrix.
Correct, right? So that is one way, but you use the concept of direction cosines mostly, right? So let us talk about this, how we can put it in a matrix form later. So let us see, right? So first of all, specify the direction cosines of the primed axis relative to your unprimed axis, right? So let us, so when I say so, this is how it looks, right? So if you look into this figure, for example, so orientation of this x prime axis, which one is my x prime axis? This one, right? So orientation of this in the XYZ system is specified by cos theta 11, right? So this is your theta 11, then cos theta 12, which is your theta 12. So this is theta 12 with respect to your y, right? And we have cos theta 13. Which one is your 13? With respect to the z axis, right? Or the z axis, whichever you say. So with angles as shown in the figure, right? So this one, it is showing the orientation of your primed axis, right? X axis with the angles with the 3 unprimed ones are given by cos theta 11, cos theta 12, and cos theta 13. Is it clear, everyone? Any question comes to your mind here? We'll come to the orthogonality conditions also. Yes. Online, any question? Okay, so though if anyone has joined late, let me tell you that these things I am doing it from Griffiths only. So any doubt that you have, if you are not comfortable in asking me, you can always ask Goldstein. Or did I say Griffith? So okay. So I'm so much used to Griffith, that is why Griffith comes first in my mouth. Yeah. So Goldstein, please refer to Goldstein, and you will get the answer to most of your queries that you have. And of course, I have already shared my email address. So any query that you have later also, I am always there. You can just drop an email.
A doubt about this.
Yeah.
I might not be able to visualize this well, so maybe that's why I have the doubt. Fixing cos theta 11, cos theta 12, and cos theta 13 uniquely determines x prime with respect to the orientation of x prime with respect to this.
Correct.
But won't we still have the freedom to rotate the yz plane about x prime?
Correct. So But yeah, so here we are talking about this theta 1, 1, 1, 2, and 1, 3, right? So here we are talking about only the orientation of your x prime with respect to the unprimed ones, right? X, Y, and Z. So similarly, we will have, orientations of your y prime with respect to your unprimed ones. Right, right. So we'll come to that. Is why, it brings us to that matrix form. So we will have 9 of those, right? So I have in my next slide. Okay. So first of all, notations you already know, the x, y, and z in terms of the unit vectors, I can write as I cap, j cap, and k cap. So these are the unit vectors along your x, y, and z or z, and I prime, y, j prime, and k prime. So these are the unit vectors along your x prime, y prime, and z prime, right? So there are direction cosines, as you rightly mentioned. So I just mentioned 3 in the previous slide. So that was only because I was talking about the orientation of your x prime only with respect to the unprimed ones, x, y, and z, right? So, but the others, the y prime and the z prime, so also they will have 3 each. So in a way, so we'll have 9 direction cosines, right? So cos theta 1, 1. So this will be given here as cos I cap, sorry, I prime cap dot I cap. So this is given as, so you can write this, right? So theta 1, 1, 1, 2, 1, 3. Similarly, theta 2, 1, theta 2, 2, theta 2, 3, theta 3, 1, theta 3, 2, and theta 3, 3, right? So cos of all of these, right? So convention is, the first index is primed by convention. You can always, mention it and, change it as per, but these are, conventionally used. So first index is the primed one and the second is the unprimed one. Okay. So now what are the relations between them? That is your I cap, j cap, and k cap. So these are the unit vectors along x, y, and z, as I rightly said previously. And I prime, j prime, and k prime. So these are the unit vectors along x prime, y prime, and z prime axis. So I prime cap can be expressed in terms of the I, j, and k by using this direction cosines, right? So, this is how it is represented. So that is why I can write this I prime as cos theta 1, 1 I cap plus cos theta 1, 2 j cap plus cos theta 1, 3 k cap, right? So the primed one in terms of your unprimed one, right? So this is for I prime. For j prime, similarly, you can write it as cos theta 2, 1 I cap, cos theta 2, 2 j cap plus cos theta 2, 3 k cap. Similarly, k prime is equal to cos theta 3, 1 I cap, cos theta 3, 2 j cap plus cos theta 3, 3 k cap, right? But again, when I say this, you should note that the inverse relations are also similar, right? So you can write the primed ones or the unprimed ones in terms of the primed ones as well, right? Okay, so now we can express an arbitrary point in either coordinate system. How do we do that? So, if you have a position vector r, so it can be expressed as your x I cap, y, sorry, this will be j cap, sorry, and z k cap. So this is your x cap, x prime I prime plus y prime j prime plus z prime k prime, right? So this is how we can use this. So prime coordinates and the unprimed coordinates, they are related by these particular equations. And as I said, like, it was valid for that unit vectors, the inverse relations are similar. So for these also, I can write this as, in a similar way, the primed and the unprimed ones, right? So now with this, idea, I can write, use this in terms of any particular vector that I have, right? So relation between components of arbitrary vector G in two systems, right? So in two systems means, one primed and unprimed, like we saw in the previous case. So we had this one. So procedure to get this would be procedure to get components of your G. So you can write this as gx. So g is the vector, right? So it can be written as gx I cap, yeah, plus gy j cap plus gz k cap, right? So that is how I can write this. So again, as I said, so your inverse relations are also very much similar. Clear? Any problem? Right. So now you see that the prime axis, they are fixed in body, right? So they are fixed in the body itself, right? And we have 9 direction cosines available, right? So as we saw, cos theta 1, 1, 1, 2, all of these. So now we can write this as cos theta ij. So will be functions of time as the body rotates. So when the body rotates, so these will be functions of time, of course, right? Now, yeah, I'm coming to that, right? So how it comes, we'll see, right? So we can view direction cosines as generalized coordinates describing the orientation of the body, correct? Because here we are concerned mostly about the orientation. However, they cannot all be independent, right? Because there are 9 of them, and we know that to describe the orientation of a body, we need only 3, right? So to orientation only, right? So the 3 out of those 6, 3, 3, right? So let us see what is the what is the discrepancy, or what is there, right? So relations between these, because if we say that they are not all independent, what is there, right? So relations between these different direction cosines cos theta ij is what? So we obtain these using the orthogonality of unit vectors in both the coordinate sets, right? So and what are these? They are these conditions that we all are aware of. That is your I dot j is equal to 0. How? Because cos 90 degree, cos 90 degrees what? It is 0, right? So that you already know, right? And I dot I is equal to 1. Why? Right? Sine 0 degree, sine 0 degree is 1, right? Sorry, cos 0 degree is 1, right? So that is what we mean. So dot product may cos comes, right? So now combining these, that means I prime and j prime and k prime. So using all of these with these known, the orthogonality conditions that we have here. So with above dot products gives the relation between your cos theta I j, right? So because all 9 of them, they are not independent of each other, right? So they are again, constrained, right? So what are these relations between them? So that is given by this summation over L cos theta L m prime cos theta L m is equal to 0, right? So this is 1. Here, of course, m is not equal to m dash. If m becomes equal to m dash, what happens? Right? So we know, so we'll come to that as well. So here, and this we can write as summation over L cos square theta Lm is equal to 0, right? And these relations between the direction cosines, so this is the orthogonality relations that we have here, correct? Yes, right? So we can use this Kronecker delta relation, right? So you can if it is not equal to m is not equal to m dash, so this becomes equal to 0, and if they are equal, then this becomes equal to 1, which you are already aware of. So the orthogonality relations, it becomes summation over L cos theta L m dash cos theta L m is equal to delta m dash, right? So this is the Kronecker delta. So there is one more delta. What is that delta function? Dirac delta. You know about that, everyone? Very good, right? So the 6 orthogonality relations between 9 direction cosines. So, right? So we have 3 independent coordinates, right? So using direction cosines as generalized coordinates to set up Lagrangian is still not possible. So instead, what we do is we choose some set of 3 independent functions of the direction cosines itself, right? So there are different sets, but there is, again, as it says, there is no unique choice for this set, So what is the most common one? That is your Euler, right? So this is the story about, why there was this need to go for this Euler angles. So that is what we see here, right? Again, when we talk about this, so relations we just derived, of course, then you can say that, then what is the point in, deriving all of these, and what is the use of these, right? So of course, we can use them to derive many other theorems about and properties of rigid body motions we can do, right? So now the goal is basically what? It is to describe the rigid body motion with Lagrangian formalism. So what generalized coordinates we require? So that is given by these Euler's angles, or the direction cosines that we just saw. So the generalized coordinates transformation described by, so we can write in terms of a matrix like you can see here, right? So that brings us to the matrix formulation also, right? So we'll see about how the proper and the improper matrix, how it works in this case, right? So I won't go too deep into it, right? So representation of A, right? So this matrix in terms of direction cosines of new axis with respect to the old is given as Aij, right? So this is equivalent to your cos theta ij, which are the direction cosines, and this matrix can be written as A12, A13, A12, 13, so on and so forth, right? So here, as I said, we have got 9, right, coordinates. So 9 Aij, but we have 6 orthogonality relations. So that brings us to the 3 independent functions, which are, we know that they are the Euler angles, right? So 3 independent functions of Aij could be chosen as independent generalized coordinates, and choice of these is, of course, arbitrary. There is no particular, we'll see about, I'll show a short video clip as well, how these, common orientation is done, but again, it is arbitrary and you are free to, choose any other, right? So, that is how. So our conventional choice is the Euler angles, right? So now this determinant, right? So we need to know something about, these this determinant as well, right? So for determinant of general orthogonal transformation, so this determinant of this matrix comes out to be, either plus or minus 1, right? So in addition to the orthogonality relations, which we have, the dot products that we saw, Aij, Aik is equal to del jk. Another requirement that matrix elements Aij of must satisfy to describe the rigid body motion. So we must have what? We must have that this determinant of this matrix should be plus 1 and not minus 1, right? So mathematically, of course, the determinant can be minus 1 as well, right? So that is allowed. However, physically, we cannot describe rigid body motion with an matrix, which has determinant as equal to minus 1, right? So physically, it does not it does not have a physical significance, you can say, right? So of course, but that is possible, right? So proper transformation, when we say that, so that is known as your orthogonal transformation with this determinant is equal to plus 1, and improper transformation is orthogonal transformations with this determinant is equal to minus 1, correct? So this is something, again, you should be knowing, right? So Euler's angles, what we have come to realize is that we can express the general orthogonal transformation from one coordinate system xyz to another primed one by 3 successive counterclockwise rotations carried out in a specific sequence, right? So one after the another, right? So Euler's angles are then defined as the 3 those rotation angles itself, right? So which are usually referred to as your psi, theta, and phi, right? So convention for the choice of rotation sequence and the rotation angles is, as I said in the previous slide also, that it is very much arbitrary, but Goldstein's choice is a convention which is used in mechanics, celestial mechanics, when you talk about the heavenly bodies as well, right? Applied mechanics, solid state physics, etc. Right? So, just to give you an idea, of course, you will come to know where these, how these rotations are done. Of course, for one particular rotation, again, you can write it in terms of your determinants as well. I mean, the matrix as well, right? So, so this is a small YouTube clip that I have kept. I just hope it opens. और कंप्यूटर ऑडियो भी शेयर किया है, ऑडियो है ही नहीं एक्चुअली, सो इट्स जस्ट कैसे रोटेट होता है that you will get to see.
My job is to make college easier because students have a lot on their
right? So first, this is the theta, this is the phi, and then the psi. Okay. So just otherwise it is difficult. I talk about rotation until and unless you see it, you are it is not very easy to grasp it. So this is how the rotation is, right? So again, all of you can write a code in MATLAB also, wherein you can easily. So okay, so that is all from my side. So any questions that you have pertaining to this topic, I can or else tomorrow's lecture also, if I won't start today itself, but I wanted to keep some time for some questions if you have any. No questions? All clear? Nothing clear? Okay, fine. Online? I'll be happy if any one of you have any query.
Sir, the also Lagrangian formalism that is used to describe the
Pardon?
So the Lagrangian formalism that we also use for the formulation of the Eulerian equation of motion of the rigid body. So what is the advantage when we take the Lagrangian formalism over without using that Lagrangian formalism, that we are going to see that by the help of the cosine angles you derive the relations of the coordinates to align it with the Cartesian system of coordinates. So what is the use of the Lagrangian formalism? The Eulerian, deriving the Eulerian equation of motion, Euler equations for the rigid body.
See, I think the entire advantage of the Lagrangian formalism was, right. So, it was covered by Dr. Sheetal as well, right? So, that advantages remain the same, right? So, it is that the entire process, every that you talk about the Hamiltonian formalism or the Lagrangian one. So, they have their own sets of advantages and, shortcomings, you can say, right? So, those applies here also, these are just tools, as I said. So your chapter 4 of Griffiths is all about, it's describing mostly about the tools that are available to deal with the rigid body problem. So, and when we say, this orientation, when we talk about, so these are the concepts that are, mostly, helpful. So that is why we are, doing it. So
okay,
that is it mostly, otherwise the formalism, so it's just the same.
Okay, understood. Thank you.
Pardon? Correct. Anyone else? क्या फ्रेम? हाँ हाँ करेक्ट. कर सकते. But again, I had kept some backup slides, but I thought, I'll stop here because I would have, like to talk about the Euler's theorem as well, right? So, but I thought, that would be too much because I'll definitely share the slides. And I also wanted, I initially thought about sharing how when we say that, the Newton's laws are, the same in all inertial frames. I wanted to show, mathematically, how these are actually same. But again, I thought, that would be too much. So it's I do not want it to be like, 1 घंटा मिला है तो जितना हो सके डाल दो ना. It's not like that. But only thing is, my suggestion is, refer to some standard book, not only in classical physics, like for quantum also, just start with Griffiths, right? So, and if you want to, say that, you are interested in physics, I think you should be able to, explain the simple concepts of, classical mechanics, quantum mechanics, and, electrodynamics. If you are able to do this in a simple way, right? So it's not about, complicating. These are there are certain complicated, problems also, right? So, but if you can explain it in a simple way, then you can say you are actually a physicist, right? So that is, try to do that. Refer to these good books. Of course, for problems you can refer to multiple and number of books, but do not ignore this, the classic books that we have, right?
Sir,
Yeah.
Sir, this Lagrangian and Hamilton part is slightly new for me. It's basic mathematical formation. So which book I should refer?
Pardon, I didn't get your question. Which book
This,
regarding what?
This mathematical formation of Lagrangian and Hamilton part in
Okay.
classical.
May I know your name?
So Vedant Gaukar.
Vedant. Griffith, Goldstein has everything, right? So for classical mechanics, refer to Goldstein. Of course, there is Landau and Lifshitz is there, but again, there are certain things that are given, directly in that, right? So Goldstein will be very helpful for you. You will get the mathematical formulation, right? And for vectors, if you want to, Spiegel is there, Sohm series, right? And for mathematical other things, I think for differential equations, you can refer to Pipes and Harville is there, right? So these are some of the very good books, right? And but Goldstein is, good enough, right? You will get most of the things in.
Yes, sir. The basic formulations of like there is a del Q and there is another del Q. So that's slightly confusing. I mean slightly new for me there.
Fine. Okay, then we'll meet again tomorrow. We will be, starting with, I'll be talking about the initial part of your, special theory of relativity, how it all started, and some basic concepts. We'll do some small examples also tomorrow in between as we proceed, right? Chalo, thank you so much, everyone. Hope to see you all tomorrow. Okay. I'll share the slides with Dr. Gaur. He may share with you, right? Okay, thank you.